Welcome to Software Snack Bites. I'm your host, Shomik of Bold Start Ventures, where we partner with dev first and SaaS founders from the first line of code. We're doing a slightly different episode today. And so while most episodes are actually a deep dive into a certain type of technology or area, this episode actually consists of a roundtable with some of my favorite folks to talk about new technologies with. So we will actually go kind of a little bit an inch, maybe a couple inches deep into areas, but we'll cover a lot of surface area, explaining many of the new technologies that I think everyone is thinking about and that's emerging today. So I'm joined by Alex Mackenzie at Tapestry VC and Ian Livingstone, who's at Snyk currently. And I consider them my personal brain trust, and I'm excited to intro them to all of you here. So with that, I think what I would start with is, the buzz that everyone's talking about, or at least I seem to say everyone's talking about, is JavaScript and then how that maps to the edge and all of that. So Alex, I'm going to start with you and JavaScript runtimes, right? Explain what they are. And let's dig into the names are amazing. Bun, Deno, all these sort of things. But what's going on? What are they? And why are they kind of having their renaissance or day right now?
Yeah, firstly, Shomik, thanks for having me. This pod is kind of very circular because, Shomik, how I know you is the last time I was going to SF, I pinged Ian and said, who should I meet? And your name was literally the first name that came up. So, Ian, thank you. And then, Shomik, I'm hoping that flattery makes you go a little easy on me.
I'm sending Ian gift cards, in the background here, Venmo requests, but
I'm just here to connect the dots, I'm creating value.
That's right.
Wow. So, on runtimes, I generally kind of have a beef with the usage of the word runtime because it's one of those infamous words in software that's used in 50 different contexts, right? Very similar to serverless or edge computing. All you really need to know is that when you're writing software, think in JavaScript or Zig or, some obscure DSL, it goes through a series of stages that ultimately enable that software to be executed, right? And those collection of stages are what's frankly a bit erroneously referred to as a runtime. So in the case of a JavaScript runtime, it's a piece of software that receives some JavaScript, compiles that JavaScript, and then ultimately executes that JavaScript within a specific environment or runtime environment, i.e. the browser, or thanks to Node.js, the server. Now, the issue is where people typically trip up is, what is this runtime environment that you're talking about, right? I think the easiest example is if you look at something like a web browser like Chrome, and if you think about a website, within that website, you've got some JavaScript, right? And that JavaScript is surrounded and interacts with other components and elements of a website. So think of CSS or HTML. So your environment, the browser, will give that JavaScript a web API to actually interact with that HTML and CSS and to kind of adapt it, right? Similarly, if you think about, my blog, mac.work, which might have, an occasional visitor or two, probably the two of you more often than anything else. Occasionally people will click on that, they'll submit a form on that, right? Events will happen. And again, the browser will give my JavaScript a way to interact with those events. It's called the event loop, right? So all of these things are provided by the web browser to ultimately enable my JavaScript to execute successfully in the browser. Now, the buns and the Denos of the world, I think, again, the two of you have heard me go on at some length about why I'm excited about them. So I'm going to try to condense it. So firstly, I think these two technologies, they take some hard opinions. They stand for something. And I think if you were, at least as an investor, I think about it, able to plot degree of opinion and CAC, you would probably find that as degree of opinion increases, your CAC goes down to some point, right? And the reason being is you're just thought of for something. Often the issue I have with specific ideas is that they feel a little incremental, frankly. I don't think Deno or Bun feel this way at all. And then if I was to put my developer hat on and speak about what I love about these projects, firstly, it's that they actually adhere to web standards, right? How crazy is it when you go into Node and you're going to make a web request, and then all of a sudden you have to use their HTTP module, whereas when you're doing so in the browser, you use fetch. So all of a sudden, the whole benefit of JavaScript is that you write once, run it anywhere, except that's not even actually the case. when you're using Node and then when you're writing in the browser. Whereas when you're working with Deno or Bun, they allow you to use the fetch API, right? So they're adhering to web standards. And then there's this term that's getting thrown around a little bit now. It's kind of maybe have an issue with it too, but batteries included. Bun and Deno are. They come with a bunch of very small utilities that, I don't know, maybe on their own don't really matter that much, but one utility will delight another developer in one way, and another developer will be delighted by another utility. And the example that I give is when you're working with Node, you'll install something called nodemon, or often will. And what it does is each time you write code and you save it, it'll run that code then. So you're getting basically the most up-to-date version of that software. You have to install that. That's a third-party application. Whereas with Bun, it comes with a flag out of the box, -- watch, which allows you to have that same functionality.
Is there like a latency component to it too? Or is it more of a latency in the sense of like, hey, you don't have to go searching through Stack Overflow or I guess now ChatGPT for like those specific things that you want to do because it has batteries included? Like, is that the benefit, or is there also like a speed benefit in the way that's been opinionated built?
It's just typically when you start a new project with something like Node, there's just a handful of these libraries that you nearly install every time. So you install nodemon nearly every time. You install .env because you're often loading .env files, right? So instead of just doing that, these projects come with it out of the box, and they come out with it in a delightful way where it integrates naturally more natively than some third-party library would, right? So it's more the convenience.
Got it.
One of the things I would add in thinking about like Node specifically, I was around when Node started. I remember world pre-Node, like writing PHP, using PHP MyAdmin to build websites. And so I also remember when, Ryan Dahl, the creator of Node, came out and was like, okay, we're going to take the V8 engine, which runs in your browser. We're going to let it run the server. Now you can program on both. And it was like the North Star was write once, run anywhere. But in JavaScript. And the whole idea was like, well, now we have what we run on the front end can also run on the back end, and now we get sharing. But it was never quite the case. And I see these projects as just points of evolution on the same curve, which is the goal was always be able to write JavaScript basically anywhere and run it anywhere. And there's just these different evolutions of that get us further and further to having to that long-term North Star. And Node itself, in its own right or not, what ends up happening with like a language runtime is you have all this code that becomes dependent upon its APIs and its foundation, right? And so it becomes very difficult. In the same way it becomes very difficult for a large company like Salesforce, it becomes very difficult to actually iterate and innovate. You get the innovator's dilemma. Well, I have this massive ecosystem supporting, right? It's very hard to move that ecosystem to a new thing. Reinventing from the ground up is going to cause a ton of controversy. So it's always a lot easier to like go to the edge and build something new and say, well, actually, we're going to leave that there. We're going to do something new for a new world that gets us closer to where we all want it to be and what the promise of Node was in the first place. And so I think it's like super exciting that this is happening. It is an interesting form of creative destruction. And if you look at Bun and Deno, like they're actually innovating in different ways. Like Bun's primary force has been on runtime improvements around memory usage and CPU performance, getting us away from the V8 engine. And Deno is the same way and was opinionated in a fundamentally different way than Bun was in terms of some of the choices. It was more about security, which was different than the performance angle that Bun took. So I'm like hyper excited about both of them. I think it's great. I'm very interested to see where this all ends up. And, in 5 years, will the average JavaScript developer be writing on a Node engine, or it'll be a Bun engine or a Deno engine or some other thing I don't even know exists yet?
How do the frameworks, how do they differ from runtimes, right? Because we just talked a lot about runtimes, but then we got these frameworks and those, if anything, actually have more buzz than Bun. It's like Next.js, or before that was Gatsby, before that it was Blitz.js, there's Redwood, like all these sort of things, right? So like these .js's literally have me like, kind of pulling my hair out, trying to understand what the hell is going on, because a new one seems to pop up every single day. And then everyone seems to be like, on Twitter at least, be like, this is the best thing since sliced bread. Like, this is what we're all using, right? So explain what they are, and then also like kind of why Next.js seems to be the one that's popping off right now.
So firstly, it doesn't help that the lines are increasingly blurring between what is a JavaScript framework and a runtime. Like that's half the issue, right? Is Bun and Deno come batteries included, and what maybe used to be provided by a framework is arguably provided by these runtimes too. So it's level set on the difference, right? Firstly, if you think about software engineers broadly, what they do is they work with a ton of third-party libraries, right? Why bother innovating on data processing when you could already import pandas? Why, if a really pretty button or form exists, why create your own, right? And frameworks are kind of the same thing. They're a series of JavaScript modules, utilities, and otherwise that help you more effectively write JavaScript and more efficiently write JavaScript for a specific use case. The use case that you're hinting here is web development, right? And then the runtime is, as we said, what actually executes the JavaScript that we ultimately write. In terms of Next.js, again, I mean, there are 100 different reasons, and I'm sure Ian will follow up with some too. But firstly, they make a bunch of strong decisions again, right? Like Next.js stands and especially initially stood for something, which was two things really. It was firstly, they're a full stack web application framework, right? I can write both my backend and my front end with Next.js. Again, the whole point is we're not having to context switch here between two different frameworks. And then they stood for a bunch of different rendering methods, the most notable of which was server side, right? So when they came on the scene, I mean, arguably the most innovative approach at the time was by React, and it was on the client side. And that enabled you to have progressive web applications, do more dynamic loading of content, etc. And then Next came along, and what was interesting is that they said, yeah, cool, we're going to start doing server-side rendering. But funnily enough, PHP and Ruby on Rails, etc., were all doing server-side rendering. So Next came along and said, we're going to keep some of what we love about React. We like its component model. We like how it manages state. But then what we're also going to do is handle the server-side rendering. And what that gave folks is more efficient rendering because you were doing it on the server side. So again, your client didn't have to deal with that. It gave people a more consistent set of assets that they were delivering because you didn't, again, as a developer, have to think, will Alex render this content slightly different to how Ian does, right? And a bunch of other features. And then, I mean, ultimately, I just don't think we could ignore that Next.js and the team at Vercel have just executed sublimely, right? Like sometimes it is just down to that.
Ian, I want to kind of tie this together, right? Because we've been talking about all this, but the hype seems to then, the way that everyone talks about now is like what's happening is edge computing as a result of all these things, right? And this is now we've reached the 5th level of the game or whatever, like we're at the promised land. So why is it so exciting, and why specifically on the front end side is there so much excitement about these runtimes and frameworks, and how is it linked to the proliferation of so-called edge?
So I think the best way to answer this question is like, let's step back and think about what development was like and what using a web app was like in the year 1999, right? And what happened between 1999, you have the Google search bar, you're using yahoo.com, and the web 1.0 era is everything was derived, rendered on the server side. There was no interactivity. And web 2.0 was really about what felt like static content, really more of like a newspaper in my browser. And it became this like interactive experience where I could comment, like Facebook's like Rides of Ajax. You get to type ahead onto Google. You get the ability to have like sort of real-time comments pop up under a photo. You get sharing. You get a bunch of these API-driven development with Web 2.0. And all along the time where we're moving is just like more and more interactivity. And the other thing that's moving is faster and faster response times and quicker and quicker performance. And the way I think about Edge, and it's like the reason it's the next step for how we build applications, is because the primary axis moving along is how can we build an app that's more interactive, how we can build an app that is more responsive, and how can we build an app that feels like it's a desktop app, but it runs in my browser, right? And what we've learned through, the last 3 phases of e-commerce, we've learned through the last phases of building apps, is we can actually tie every percentage increase in latency or decrease in latency as the page renders to dollar value. Like we know that for every 1% faster page loads, I can tie that directly to how much more money you're going to make if you're selling shoes, right? There's something about performance and the look and feel of an app as you use it that actually makes us want to use it more. And so edge computing is really about 2 things. One is how can we get the bytes closer to the customer? So when we render, how we get the first render faster. So when you get that page, it feels faster. And the other part that not a lot of people talk about, but is important to talk about when we talk about edge, is about data residency. In a world where we have GDPR and all of those things, we're talking a lot about privacy. How can we ensure that the data stays as close to the customer, or in another way to say that, it stays within the residency of the customer? And the whole idea behind edge computing, which I'll say is an overloaded term, and I'll actually define in a second, the whole idea is like, how can we get the compute that currently happens inside the Amazon data center closer to, the customer in Ireland with Alex, closer to Shomik in San Francisco, and closer to Ian in Halifax. So you all have that, like, it feels like it's just running on my local laptop experience, but you have this massive like computer behind you serving it up. That's what this is about. And it's a really hard problem to solve. And the truth is, it's a problem that's easier to solve today when you're just rendering a web page. It's not easy to solve for like, how do I get the data to the web page? We can talk a lot about why that's an unsolved problem. But like, this is the first place where, well, if we put the compute at the edge, the thing that we can actually minimally compute at the edge is all the static content. And we can give that to them. And we can also cache a bunch of stuff related to that user at the edge that we couldn't before, because we know that all the requests are going to come in through this like one edge node. And so what's kind of happened is, despite the fact that for years we've had big companies that build up points of presence, like the reason Google's so fast is they built this massive network, this massive ecosystem of data centers, and they've invested tons of money into setting up proper peering and global DNS routing to ensure that you're always getting the first byte as quickly as possible, which is why you keep going to google.com. And now what's happening is we have providers like Vercel, Cloudflare Workers, and others out there democratizing what once was a Google or Facebook only thing into the hands of tons of web developers everywhere. And that coincides with things like Next.js and React, because that now put the power tools of, how do I take this website, right, componentize in a way that I can scale at the complexity of the app, and then how can I move the rendering of that from what was the client side into the server, so I can have a program experience that was similar to Ruby on Rails with a user experience that's highly interactive and as close as possible to the user. And that's why this is also interesting.
We covered front end, but also, frankly, in some back end use cases. But I want to dig in more into the back end side, because the funny thing is, it's not just the front end developers that are really fired up about Edge. It's all the back end folks as well who are really fired up. And they're just like, oh my God, now we can do Kubernetes on the edge. We can deploy ML models on the edge. This seems to be the first time that both these groups seem to be, agreeing on something. What is enabling this? Why is it happening now? Why are both sides getting excited?
It all comes back to that same thing I first said, which is like, how can I get the answer as close as, like, the thing that's computing an answer as close as possible to the person that's trying to receive it, right? Like, fundamentally, that's what's the top level thing. And what's prevented us from moving compute and workload to the edge previously is just the way we architecture our app. So if we sit back and think about the way we build apps in the early 2000s, it was PHP and a MySQL database, right? And it was really hard to decompose that. Everything was intertwined, right? In order to render a page, you did MySQL calls between HTML. It was a nightmare. So it was very difficult to take an app like that, or even in Java with MVC, it was very difficult to take that and decompose it into different components where you can put different components that are responsible for different things in different places. And so now the reality is, we've always had the desire to have like hyper responsive applications, and we've been building the technology all along the way to enable that. The other thing is, our architecture of how we build our apps has been deeply componentized. So instead of having this one giant glob of like a God thing that .jar file that we're trying to run everywhere, we now have, microservices that are componentized, and if done properly, they're well bucketed, and you can separate them. And so you can start running different pieces of your software in different places. I like to describe this as, I always think of the e-commerce app. In an e-commerce app, you kind of have like, you got your catalog of stuff, like what are you selling? You've got your user data, which like, who are you and what's in your shopping cart? And then you've got, your ordering mechanism. And if you think of those three generic components, well, you can do all the rendering of the website at the edge, no problem. And you can keep the user data at the edge, or at least cache at the edge, because that doesn't change per request. And you can keep the catalog at the edge. And you can keep the user's shopping cart at the edge. But the thing you want to keep central, because of transactional requirements, you don't want to ever oversell something you don't have, right? If we only have 5 pairs of great hats, then we want to only ever sell 5 pairs of great hats. So we don't want to sell 6 of them and then one customer never get it, right? Or lose the fact that a customer ordered something. And so because that's transactional, that needs to be done centralized. So you can move these different pieces around in a way that you couldn't before, because we've taken what was once this really gob of glue mess and turn it into a bunch of components, and we can move those components to different places. And interesting enough, because we can do that, we introduce new functionality, like the ability to do a machine learning model. Well, now half the data, or most of the data, is at the edge already. So why would we even put it in the centralized cloud when we could have put it close to the customer? And the complexity and the multi-billion-dollar problem to solve for somebody in infrastructure is, how do I ensure that the development experience for the developer building an app that could have data basically anywhere is simple enough for me to understand that I can build a complex application and scale it. And there's a mechanism under the hood that is moving the appropriate data to the appropriate places and dealing with the transactionality.
The minute this podcast gets posted, VCs are just gonna, like money will just appear in Ian's bank account and it won't even have a name associated with it. It'll just, and then like a handwritten note will appear, so.
Yeah, I really missed my moment to be like, oh, by the way, just one more thing. I don't have a company on this, but yeah, there's definitely like a huge opportunity.
Yeah. Let's move into the next area that I want to chat about. So that's languages. Alex, you've written actually quite a bit about some of the new languages. You have a great piece on Zig, which we'll link to in the show notes. But TypeScript has had a massive growth recently. Zig, obviously. Meanwhile, the existing languages, JavaScript, Ruby, Go, are obviously still very high in the rankings, still being adopted. Lots of people are using it, but the slope of the curve for TypeScript and Zig and some of these other languages is quite aggressive, right? And quite rapid. So what's driving that trend? Why are they exciting? And why are people using them?
Yeah, I mean, on the programming language side, what I'll do is I'll break them down first, TypeScript, Zig, and then we can kind of hypothesize. So TypeScript is literally just a superset of JavaScript. And what that means is you get all of JavaScript and then some. Really is just TypeScript's typing system. So when I create a variable, when I'm writing TypeScript, I have to state the type of the value of that variable. So if my variable is, I don't know, podcast host, right? I have to say that value is type string and the string is Shomik. It's not type number, it's not type Boolean, right? You have to be explicit. The reason for that, I mean, twofold really is firstly, it's just much easier for your coworkers to read your own code and frankly, for you to read your own code yourself when you're more explicit, right? When you know what the various types are supposed to be within that code. And then also tooling actually gets augmented as a result of this explicitness. So all of a sudden your IDE can do code completion a whole lot better. It can actually look for type errors. It can do error hinting better. Right? Like you've augmented the IDE. Zig is a lot of things, and we could do an hour on Zig here, but it's at its core a very simple general purpose programming language that I do think will take on C over some period of time. You heard it here first. My favorite feature of Zig really is just its simplicity, though. I mean, you're probably seeing a theme here, but for context, in Zig, your code literally executes line by line. And that's, again, not very intuitive for people, or at least people that haven't spent a lot of time with JavaScript. But most programming languages, your code doesn't actually execute line by line. I mean, JavaScript has function hoisting, for example, which can do some really strange things when you're not expecting it. And then also Zig is a tiny language. It's like a 500-line PEG file, right? Tiny. And the reason being, the creators only wanted there to be one obvious way to do something in Zig, which again just improves readability. So there's this famous lore of Zig, which I wish they didn't really backtrack on, but they did. So anyway, where for a long time there was only a while loop in Zig. There wasn't a for loop at all. And maybe that isn't like a mic drop moment, but it is for me. And the reason being that they were like, well, you can basically do everything you can do in a for loop with a while loop. So we're just going to keep the while loop. We're going to keep the language simple. If I'm hypothesizing on why I think there's been this resurgence, I think firstly, there's the investor hat on answer, which is like Next.js, as I said earlier, kind of showed you that if you own the language, there's a ton of value capture downstream. There's CI/CD, there's analytics, there's storage. Microsoft, I mean, maybe that's what they're doing with TypeScript is like, well, guess what? We were losing that battle maybe on the Python side with JetBrains. So instead, let's build TypeScript and let's make that most native to VS Code, right? There's strategic reasons to own a language. Google's doing the same with Dart. And then from a developer perspective, I don't know. Like you look at a lot of technologies like Nix is another great example where they feel like overnight successes, but they're not actually. And the curve will tell you they are, right? The curve will look like that slope as you described, Shomik. But really what's happened there is all the documentation's finally been written. The tooling's been built. The language servers have been built. The third-party libraries have actually been built. Like Zig is pretty bare at the moment, right? So I think ultimately what it is that eventually these languages also actually become viable and plausible and usable, frankly.
By the way, one thing I'll add is so Funny story about for loops. When I was taking my first intro to programming class, I didn't know what a for loop was. And so I literally thought it meant for loops. And so I was like, so what happens after the first loop? What triggers it? Needless to say, I've since been corrected in that. But sorry, Ian, I think you were going to say something. So
no, I mean, that's amazing. And now that I know that, I'm never going to let you live it down. Yeah, I think one thing I'll add is it's important to think about languages are full of trade-offs. There's a trade-off like JavaScript versus TypeScript. There's a trade-off like types. We went through this phase as an industry where we thought, well, I don't need types. That was the whole, JavaScript trend was, I don't need it. I can write a lot of code a lot faster. And that's true. And then you go to scale that code base. You go to put more workload on it, more customers using it. You go to add more functionality. And quite quickly you realize, oh, actually, I really do need types because I don't have enough context as a human to understand how this program is supposed to work. So I need something to tell me that I'm doing something that's wrong. And so a lot of the time, there's two things that go on from my observation. One is there's sort of TikTok where we go between like strongly typed to like, oh, that's not productive enough. So then we invent a new thing that's less strongly typed. And the other part are trade-offs for like new runtime environments. So for example, Go is an amazing language for writing a web service, like just like an at-scale web service. It's a very productive language for doing that, especially if it's going to be around for a while. If you're going to invest in it over years and years and years, perfect. But it's a terrible language for doing anything in machine learning. And you have all these trade-offs. I talked earlier about this ecosystem effect where you have this like massive house that's built and you're like stuck trying to support it, while there's all this creative destruction going on and trying to find new entry points to make some new emerging task that we have more successful. And sometimes there's new things that look backwards and say, well, there's this, like Zig is a great example. There's this amazing ecosystem, and I won't say amazing, let's say big ecosystem of C++ programmers and code out in the world, but it's been left in some design decisions in the 1990s. And that's made it really hard for new engineers to want to get up and using it. There's productivity impacts. And then Zig comes along and says, hey, we're like C++ compatible, but we're extensible. So you can start writing new C++ in your existing retrofitted code base with us, and you get all these like productivity improvements that have always been these like hard problems that make it difficult for a new developer to want to get started, especially if you use like npm install, or if you use go install, or if you used any of the new tool chains out there, and you go back to C++, you're like, this is esoteric, difficult to understand, brittle, and way too low level. And so Zig comes in and says, well, what if you could have the C++ ecosystem, but less of that? And I think that's a lot of what's going on is that you have existing tasks, big ecosystems, there's an opportunity to improve. And oftentimes it looks like, well, a new language actually, or new tool set will actually solve all of this. And so the same thing that happens in framework land and library land and SaaS software happens on the language side.
It's literally happening with Mojo as well. Their tagline is it's Python with the performance of C. The Python ecosystem is already there specifically for machine learning. Let's not reinvent the wheel. Let's just take two great entities.
It's a fascinating area, and frankly, one that might warrant actually even a full podcast on itself, just because a lot of the concepts there, I think we could dig much deeper into. But one of the things I want to move into is actually observability. And I think what's interesting now is there's, again, this big movement for new tools. Obviously, some of it is cost related, right? But others are related to now there's kind of standards that have come in place, or frankly, old technology, like we'll talk about eBPF, but that has now somehow had a resurgence into being a new technology, which I'm not quite sure how it happened or what caused it. But, Ian, let's start off with you, like kind of what is eBPF? Why is, the stuff that's happening around open telemetry important? And how are these being used to improve observability?
So I think we have to have a history lesson again, which is we go back 10 or 15 years or 20 years when we think about what did it look like to get data about how my app was performing in production. Dude,
this is like hardcore history for programming. Like if we only had drinks while we were doing this would be perfect.
I mean, I've always wanted to be Dan Carlin. Like if I have my fallback position, it's podcast host of like a hardcore history type show. You want to learn about Rome? I've got you covered. If you look back and you say, well, one of the biggest challenges in building an application, getting into production, and then having a workload against it so customers using it is understanding what's going on. And for a long period of time, that's been a relatively manual process. And the level of depth of that observability, that insight you have into how your app's performing, was at different layers of abstraction. So 20 years ago, we'd have some good insight into what logs were coming from the service, We'd have some good insight into what traffic was going into the service. We'd have some good insight into like what CPU or memory was being used by the service. But we don't have actual insight into like what literal code is running and a good way to capture it. Scroll ahead 10 years and we have libraries enable us to do those things. We had like metrics and timers and traces. But all of that stuff then went to some proprietary API. If you're using Datadog, we're using the Datadog library. You're using Prometheus captures, it's all Prometheus stuff. And there is this fractured ecosystem where basically once you made a bet on who your telemetry provider was going to be that you're going to use for observability, you were very much locked into their ecosystem. And open telemetry is really interesting. BF is really interesting because they're kind of two of the same things. eBPF is trying to sell us the idea of auto instrumentation. It's the idea that I don't have to instrument my app. I can have this thing that runs as a part of the kernel capture traffic and things that are going on inside the app by unresolving symbols and looking at the syscalls to capture telemetry, which it then sends to an open telemetry service and then basically puts it all back together to try and give us a picture without the developer having to do anything. And so the promise of eBPF and open telemetry together is the idea that, well, as a developer, I don't have to instrument anymore, or I don't have to instrument to the same degree. I get more things for free out of the box, and I get more insight, and I can switch my providers. That's what's going on. And obviously, there's a lot of strategic things of different partners and different providers in the ecosystem being pro or not, as all of these open standardization things are driven mostly by industry and driven by how do I retain or gain market share. But long-term, the value prop is eBPF is this way to basically program probes in the kernel to listen to events that are happening at syscall level, that observe what's going on inside a process. Those can be network events. Those can be like a call to read a file or whatever. And the ability to, like, once it reads that state, send that state someplace for some other process to pick up and then forward someplace else. And that's where OpenTelemetry comes in, where the place is being forwarded to follows a protocol like OpenTelemetry. Now, there are auto instrumentation libraries that are code focused, so you don't have to do eBPF with OpenTelemetry. But the promised land is you get auto instrumentation at kernel level with eBPF, and you have OpenTelemetry. And so the burden to actually start getting insight, the amount of investment I have to make as an engineer or as an VP of engineering in terms of getting a good setup to understand the health of my production stack is significantly lower. Now, there's other interesting use cases of eBPF, like there's a lot of discussion around runtime security use cases of how could I use eBPF to potentially stop attacks or detect out of policy violations. Those things are still, I would say, largely science fiction, but interesting. But certainly the most interesting use case of eBPF today is being able to capture data that you couldn't capture before and capture data in a more performant way we couldn't capture before because it's happening at a lower level in a more optimized part of the stack.
What I love about eBPF is it's like the best example of a very specific technology that was built for a constrained environment, had to innovate a bunch because of that environment, i.e. the kernel. And then because of those innovations it made, e.g. the eBPF compiler, all of a sudden there were all these other use cases, e.g. actually doing runtime security because of the innovation made due to those constraints, right? Like we have that with V8 and JavaScript. Same example. Or I don't know, the Slinky was a stabilization spring before it became the thing that you push downstairs. Constraints breed some pretty exciting innovation.
That may be the first time I've seen Slinky and observability tied together, but Alex, that's pretty good. I'll give you an award for that. But one other thing that a lot of people, Snyk has been big on this too, is what's called OPA, which is Open Policy Agent. So we just talked about open telemetry. Why don't we just talk about the other open thing, which is Open Policy Agent? So what's the deal? What's going on there? What's that enabling?
So Open Policy Agent actually comes from the land of Kubernetes, which is a way to say, how can I govern, write policy? So as a DevOps platform engineer, how can I write policy about what should be allowed to happen inside my Kubernetes cluster? And the interesting thing of OPA is that it actually has an underlying language called Rego. And this underlying language called Rego is a Prolog derivative that is nice for writing out statements about truth. I can write a rule and I can write all the things that have to be true for that rule to be true, which is a good way for me to want to express policy. So if in order for Shomik to have access to a process or Shomik to have for HTTP traffic to some ways, it has to have, a certain header on it. It has to be on a certain port. It has to be from a certain ingress point, right? Now, the nice thing is that OPA And Rego is an open source language. And so very quickly, it started to become this sort of standard for expressing policy rules. We didn't have anything in this space that wasn't vendor specific prior. And so with the rise of Kubernetes and the rise of the Cloud Native Foundation and Opal being a part of that, that's also meant that Rego is now more prolific as well. So if at Snyk as a vendor, when we think about, well, we need to enable our policy engines, our rules to be extensible, what's the most natural thing to exist, right? I'd rather not invent a new language. That seems silly, right? I don't want to teach someone, have the burden of learning on our customer to learn something new that doesn't provide them any new value. So for Snyk, we've started to completely standardize a lot of our policy on top of Rego because, our customer base already understands it, and there's no learning curve really for those that understand it. And more importantly, there's tons of resources in the world to support these folks.
We're going to move into the topic of encryption. So this is going to be a fun one because, Alex, I'm going to start with you. But the best part about this is Ian actually co-founded Cape Privacy. And so literally like anything you say that is wrong, Ian will know immediately. And so I kind of like putting you in the hot seat. But one thing I know is you wrote about secure enclaves. I know you do your research very well. And so dive into those. And then Ian, if he gets anything wrong, you can call Alex out.
Shomik, I'm just mad because you literally stole my joke. Yeah, I've been pretty obsessed with Andrew Trask's idea or phrasing for some time, which is this idea of getting to a point where we can pip install the world's data. Think about how exciting that is, right? Like if we literally had a data set of the world, think of the models we could train, think of the solutions we could build, think of the personalization, etc. But obviously to do that and to do that at scale, we need to work with that data safely. We need to ensure anonymity. There's a bunch of constraints that make that very difficult. So I went down this rabbit hole of, asking myself what technologies need to exist to make this happen, right? Differential privacy, federated learning, etc. Obviously, we have ways to protect data at rest. We have ways to protect data in transit, TLS, etc. But the holy grail has always been protecting data as it's in use, because it's super difficult to do if you think about it. Because great, we can keep things encrypted for all those other stages, but when we actually want to process some data, if I have a function and it adds 2 data points, 1 plus 1, great, that's easy. But if those data points are instead ciphertext, all of a sudden that expression and completing it becomes pretty difficult. That took me down the rabbit hole of secure enclaves. I looked at a number of other methods, right? Homomorphic encryption and all its various derivatives, which I'd actually love to get Ian's perspective on. I don't think I ever asked you. But ultimately, I was led to secure enclaves because what secure enclaves ultimately enables you to do is you do still decrypt this data. You just do so in a secure environment that is isolated from a bunch of malicious threats and constrained too, right? So all of a sudden, this environment doesn't have internet access. It doesn't have persistent storage. It's constrained. It doesn't have shell access. So all of a sudden, common attacks like side channel attacks or memory scraping or a bunch of other threats are mitigated. And then the other key point is that it can be cryptographically attested that it hasn't been tampered with.
Well, Ian, there's homomorphic encryption, there's federated learning, there's multi-party computation, there's differential privacy, right? Everyone's heard all these terms. Now we're also talking about secure enclaves. It makes people's heads spin. You have the hard problem now of condensing all of that and making it into why is this stuff important and why is it interesting?
I was recently recorded an episode of my podcast with Tim Chan with Mike Malone. And so he described Enclave specifically as solving the last turtle problem. And I thought that was genius because if you think about it fundamentally, there's always been this question of like, well, who am I trusting? If I were to send Shomik information, we didn't have TLS and anything, who along the way is going to have access to information? And to get started, we had this ability to do TLS, right? SSL, HTTPS. This ability to say, well, we'll establish a key together, and we'll do a song and a dance. There's a certificate. And if I trust the person who gave you a certificate, then I trust that you are who you say you are. And therefore, we can establish a session and I can validate your keys with the fact that your certificates were signed by someone else that I trust. And now I can send you data over a channel that we both agree is trusted because I believe who you are. What we've never had is an ability to trust the thing that's doing the computation. right? So we can trust that where it's going, that the data as it's passing over the network is encrypted. But as soon as it gets to the other side of the network, it's unencrypted inside that computer. And what enclaves really give us is an ability to attest two things. One, what is that computer on the other side? And what's the environment? What's it allowed to do? So we can say, am I talking to an Intel enclave? Am I talking to a Nitro enclave? Now we can test that cryptographically, because etched into, in the case of Intel enclaves, etched into the wafer, like the literal circuitry of the enclave, is an encryption key that only Intel has access to, right? In the case of a Nitro enclave, well, the Nitro enclave is established and encrypted using a key that only Amazon has access to. And so if we're now able to answer a question of, well, who am I fundamentally trusting? And that wasn't possible before. And the second thing that's very interesting is our ability to then say, well, what code's running in that thing? So if I trust the code running in it and I trust who's running in it, then I can trust that sending my data from my place, whether it's a picture of my eyeball or the password to my bank account, over to this enclave, if I know what code's running in it and I know who is it fundamentally has the encryption key to decrypt it, then I know who I'm trusting, and I can send it over the wire and say, okay, I know what's going to happen to it with decent probability, low risk. And so that's the fundamental innovation of enclaves. In the case of a secure enclave in the context of cloud computing, it solves this fundamental problem where I don't have to necessarily trust the person I'm buying software from to be secure if I trust the code that's running in the enclave and I trust who's providing the enclave. And that changes the risk equation for what data a customer may be willing to provide to a cloud service. And so that's the massive business opportunity. When it comes to these other sort of techniques that you mentioned, differential privacy, homomorphic encryption, what there really are is a way for dealing with the trust equation. And some of them deal with it by removing data effectively. So differential privacy is a good example. Let's say I have a data set of pictures of eyeballs, and I don't want it to be possible for me to pick out Shomik's eyeball, but I don't want to lose the unique data that Shomik's eyeball provides that data set. And so basically what you're doing is you're saying, we're going to try and keep the information in the data set cohesive, but we're going to try to remove the uniqueness from it by adding noise, random data, basically. So in the purposes of using it for machine learning, I can say, well, I can still create a model that's valuable, and from a data distribution standpoint, still provides the value the same undifferentiated data set would have given me, the plain text data set would have given me. But I've removed the ability for me to pick out any one person from that data set. And so that's one way. So that's one way you deal with the trust equation. Because I wouldn't necessarily trust, in Canada we have Lawton's drugs. I wouldn't necessarily trust Lawton's drugs to have a picture of my eyeball or a section of my eyeball. I don't know what they do with it, but they can definitely have some unique information from it to help us train, a diabetic retinopathy model. When it comes to things like homomorphic encryption is totally very similar to secure enclaves. It's a how can I compute on encrypted data problem. It is 100% a hard math problem. And in order for it to work, we will have to invent and are inventing new mathematic models and processes to enable us to do it. And basically the way homomorphic encryption works is if you encrypt something and you encrypt something else, if they're both encrypted homomorphically, it means that you can perform operations on the encrypted data. And at the end, when you decrypt the data, it'll give you the right answer. But in order to do that, it's very complicated. There's other ones like multi-party computation, which have trade-offs, but are basically doing the same thing. So in homomorphic encryption, you have what is a hard math problem. In multi-party computation, the fundamental problem there is, well, you're not relying on inventing mathematical techniques such that every time you compute it, at the end of it, you can unravel it and you have the right answer. You're using the network to basically make trade-offs. So you're having multiple people have little parts of the answer, and then you use the coordination of computing something across these little parts, and you constantly add random noise as those computations go on to basically try and manage how much information anyone at any one time has, so that at the end, when you bring all the parts back together, you have the right answer. And so these are all different methodologies we're basically trying to establish and deal with, how do I protect myself or whatever data I have from someone else getting a hold of whatever it is that they think they're getting a hold of? How do we enable us to actually bring those things together in a trust model that makes that everyone can sit back and say, you know what, this is reasonable to us. We accept the downside risk here because the high probability of that occurring is so low that it's a reasonable trade-off for me, and the upside to this is good.
That was quite the masterclass, and I think I think couldn't have asked for a better rundown on that. So let's move into the topic du jour that everyone, of course, is talking about, and I kept this for last so that for anybody who's listened to the whole podcast so far, like now you finally get the questions that you had answered about AI. And this is obviously what everyone's kind of thinking about and talking about. So I think the first question, and Alex, I'll ask you this. We've heard a lot about LLMs, but then you have AutoGPT, LangChain, Baby AGI, all these things coming out that are these so-called autonomous agents. And so what's the difference between what people are currently doing with LLMs and then what agents could bring about in the future?
Yeah, so LLMs like GPT, Claude, Bard, etc., are the core component of these agents, but then these agents also have some other features that make them agentic, so to speak. So the three are they can plan, they have memory, and then they can also access tools. And I think the best way to kind of walk through these examples is through a real query that you could give something like engineer GPT right now, right? So imagine we said something like, create a multiplayer game with a JavaScript backend. Within that game, I want the 4 players to be my 4 closest friends. And then what I want you to do with the front end is I want you to write the HTML, the CSS, and then can you please use, and you always have to say please, right? I don't know if you guys fit in that category, but I most definitely do. Can you please use something like Three.js, a library like Three.js? We'll break down the 3 different stages here. So on the planning side, you kind of even heard me do it in the example, right? I inserted commas and full stops. And effectively, that's what the model is doing too. It's breaking up that large query into a series of subqueries or subtasks. To say, for example, again, the first one is create a game. So it starts doing that with the JavaScript backend. Maybe it generates some code as part of this planning process. And then the other key part of this planning process is that these agents can be instructed to self-critique themselves. So say, for example, it generates this JavaScript backend. Maybe the self-critique is this the most performant JavaScript backend that you can create? And if the model says, no, it's not, then the model is told, well, make it more performant. And the next time you generate code, make sure to do the same again, right? So the model is like improving as a result of this planning. Secondly, in the query, I said, hey, include my 4 closest friends. Like maybe GPT is trained on that, but I'd like to think it doesn't know who I am, nor does it know who these folks are. So the way that we give these models kind of external memory is through these vector stores or vector databases, right? So all of a sudden, these agents can query these external memory banks, so to speak, and actually leverage that data as context. So all of a sudden, maybe I do have stored who my 4 closest friends are, or some proxy for that measure. And then finally, I included the Three.js library. And what the tool use is that you could, say, for example, use external tools, like external APIs. So I can make something like a request. I can fetch the documentation of Three.js. And I can make sure that then the code I'm generating is the most up-to-date Three.js code, because for what it's worth, as a side note, that Three.js changes every second day. It's kind of a pain. So all of a sudden, we've got this agentic behavior as a result of these 3 steps.
I think one of the interesting questions is how do we govern these things? And so a question Shomik has asked me multiple times is like, how do we know what's going on? How do we know what these agents are doing and why they're doing it? And how do we know what works? And I have a multi-part answer. And I would first say is like, we actually do have the tools to understand and observe what these agents are doing, right? We talked earlier about APM, OpenTelemetry. Well, OpenTelemetry, if you plug OpenTelemetry in a piece of code that's agentic, it's going to track all the HTTP calls and all the decisions that are going on a code level. And so you really have to sit back and say, well, explain for who and what parts need to be explained. So I can tell you today that the output of the LLM was X. We then use that output to go into this other thing, and then the output of that was this thing, the output was that. So we understand that layer. What we don't understand is why the model generates the answer it does. If I prompt it with, tell me about the 23,000 different ways that I could slice an orange, I can't explain exactly why the model generated the answer it did. I can tell you structurally, architecturally, why the model has that properties, why transformers have these properties, and why prompting results in these interesting properties. but I can't tell you why that model specifically generated that answer. We just can't do that today, except to say that the model has been trained with a certain set of weights, and those weights are the result of millions of passes, forward and backward passes of training, as a result of feeding data sets into the model over and over and over again, and then wrapping that with some very interesting layers to create the properties that we see today. So I would say one is we actually do have a good understanding in the abstract. We do have an ability to track what the answers of these models are. And we do have a capacity to understand where the data is coming from. But I can't tell you exactly why this specific version of this model generates this specific answer. And I certainly can't compare two models without ad infinitum comparison of all possible prompts I put into it and comparing all possible answers as to what the difference between model A and model B will be. Because it is actually what we're doing in training these models is we're taking, basically doing a lossy compression of a huge amount of data, putting it into a matrix, and then extracting that from said matrix based on some parameters that we give it. And so we can't explain specifically why this set of numbers in this giant matrix are going to result in some answer.
So what do we need then? Just the right interfaces? Like, I mean, Perplexity helps that you see references. I think it's like very early, but do we not ever really solve the problem of this is exactly where this answer is coming from, but we just build better interfaces to give people confidence in the recommendations?
So there's this question of determinism in models. And so at some level, this is the world of data science, right? Which is the model adapts and tries effectively, and through the training process, we try to create generalizations. And so you can say, as a part of the pairs, for the training pairs, you can say input X should result in output Y, and output Y is like a tuple of here's the answer and here's the source. But through the training process we have today, I can't tell you what happens for all of the test cases that I'm not testing, for the non-tested test cases, for the non-input, right? It could generalize a concept and it will be able to tell you exactly what source to generalize that concept from, or is it going to merge a bunch of these things together? So we can't do that. So this is an active area of research. And there are people far smarter than me that are far more capable trying to investigate, like, how can we tag the input data we give it, that we train on, such that when it outputs, we can source that back to the source. And I think what we're going to find out is that this problem is hyper complex, because if you think about it, we're trying to attach a third dimension effectively to how these models perform, which is don't just like encode data efficiently and enable me to retrieve it efficiently, but also tell me where that data came from so that I can cite it. And that's very difficult.
Yeah. One thing I want to move into actually is fine-tuning and inference, and then also its impact on prompt engineering, or not impact on prompt engineering, I guess. But I imagine it does have an impact. So Alex, maybe first start off with you on the fine-tuning and inference, and then any of your thoughts there. And Ian, would love to hear your thoughts as well after that.
Yeah, this will be a pretty quick one for me, for once, as an Irish guy that usually is given what's known as the gift of the gab. But fine-tuning, I had to get that one in the podcast. Fine-tuning is really, you want to understand why you do it first, right? And the point being that, again, we can remember what all these LLMs are trained on. They're trained on a bunch of data, open data on the internet. But that most definitely isn't all data. And so if I'm building a specific or want to leverage a specific model, I might take something off the shelf like Llama, but then maybe it's actually not performing as well as it should. So perhaps I'll actually train it additionally on some of the data maybe it's already seen, right? Different derivatives of it. Or maybe it's never been trained on some data. Again, example being like, hey, who are my 4 best friends? I don't think we'll ever train on a large enough data set there, but you get the point. So a company might have its own specific internal data set that it wants to train this off-the-shelf model on, and that's what fine-tuning is. And then inference is, yeah, it's pretty simple, right? It's just literally the prediction that is made when you've actually finished creating a model. You've got a model in production, so to speak. You pass it a given input, and it makes a specific prediction.
Ian, we'll hop over to you. What do you think?
Listen, I think like at the end of the day, fine-tuning is super interesting. We have this ability to take a bunch of knowledge, compress it into a model, and then say, hey, and fine-tuning specifically is about like blowing up the last layer of a model and then basically retraining on a new thing. So it's like we've trained this model to be able to understand cats, dogs, log houses, trees, insects, right? And there's a bunch of things about cats, dogs, logs, tree houses that are generalizable, like the model learns. And then we can take that information and say, now, actually, I want to take the fact that you understand that model, I want to train it on my specific problem, which is maybe differentiating between bikes and dogs. And the model has already seen a lot of different types of things. The model already has the ability to generalize and identify certain concepts, post certain unique values because it's been pre-trained. And so now, instead of having to retrain a model from scratch on a much larger data set, I can take a much smaller data set and train this generalized model on my specific problem. What we've learned is it's both cheaper. We've also learned that it's faster and it ends up with more accurate outcomes. And so this fine-tuning process is one of the things that's making this current open source model movement really quite interesting, is the idea that there's all these really highly trained 80% for everything models in the world that I, as Joe Blow or Susie Shear or whatever, can then take and train on my specific problem, and I can get up and running it at 10th of the time, 100th of the time. And oftentimes with the tool sets and the new SaaS platforms that are available, I don't even need to understand how you created the model. I just need to give this fine-tuned platform my unique problem space, and it can train it for me. And so it's deeply democratizing the access to deep learning. And we have a long way to go here. Like if ChatGPT was the first inning of what transform architecture can provide, or Stability AI is the first, then 10 years from now, or once we have all of this has gone its way into industry, there are going to be a lot more specific places where we were able to solve problems in a way that we weren't before. A problem where we'd have like the human would have to be hyper responsible for this section because the computer can simply not do it, can't reason about it. Now we have a thing that can reason about it 90% of the time, and the human has to do 90% less work.
So the last topic I want to cover here before we kind of wrap is web GPUs. So maybe Alex, I know you wrote about that. Why are they exciting? What are you excited about with web GPUs?
So I'm going to give you a hard time. It's WebGPU, firstly. So there you go. That one's for free. I mean, yeah, WebGPU is a web API, right? We discussed these earlier, that the browser gives you a set of specific APIs that enable you to do specific things. And in this case, it's a modern web API to work with your underlying GPU on your machine. Now, we've had this for a while. We've had, I think, WebGL since, 2011, 10 or so. But the issue with WebGL is it was created, it's web graphics language, right? It was created specifically for using GPUs for that graphics use case, right? The graphics pipeline, rendering graphics on your browser screen, specifically within the canvas element, right? But what some pretty enterprising people did, or at least the apocryphal story goes as far as NVIDIA is concerned, is that they started to think that, well, wait a second, if all graphics is, or a big part of graphics is, coordinates that we then color and shade, et cetera, through this pipeline, they're vectors, right? They're points in space. And what else are vectors? What we use in machine learning, right? Weights and biases. So all of a sudden, they were able to repurpose these GPUs through the graphics pipeline. So they treated this machine learning data as coordinates to end up doing the same thing, right? To run it through the computer graphics pipeline. So some years passed, and then we got given this web API called WebGPU, which gives you two pipelines. So one, we can now use more modern specs and more modern GPUs as a result for rendering graphics, thanks to WebGPU. Amazing. But we can also, or we're also given a separate pipeline for that computation, whether that's machine learning or other general purpose computation.
We covered so much in this episode. It's frankly amazing. And the breadth of knowledge and expertise here is awesome. This is why I love talking with you guys. I would say out of all the things we covered and everything we discussed, maybe Ian, I'll start with you. What's one thing that maybe we didn't address that you're like, oh man, this is exciting and I would love to chat about it?
One of the things I like to think about, and I don't talk about enough, is actually just what happens as our fidelity of data increases. So I often think, what have we really been doing for the last 30 years of computing, 40, 50 years, is taking a bunch of things about the world and figuring out how to describe them in a way that a computer understands so we can compute on them. And LLMs, machine learning, deep learning, all this stuff with images, just a new way for us to take a whole data set of stuff that we could previously not compute on very well and make it more computable. But what's the end gap? Where do we end up? Where and how do we get there? And so like in our industry, I often think about security, and security is very much a data problem, which is like ultimately what you're trying to do in security is you're trying to model the world of stuff that could go wrong, and you're trying to prevent those things from going wrong. You're trying to get ahead of that. And today it's hyper reactive because we're not deep into the workflow. So what happens is we have like higher fidelity understandings of the world around us. And what does that mean? That is a very theoretical, but I also think it's like ultimately I just come back to every time. It's like there's probably two things that are true about computing. One is we want more interactive experiences that feel more like we're living them, a lived experience. We're spending less time. They move at the speed of thought. And two is we're constantly increasing, trying to increase our ability to describe the world around us and computing and present that in a way that truly assists us in doing what we want to do every day.
Alex, what would that be for you? What did we not discuss that you're excited about?
If you check on my blog, firstly, Mac.works, and if you /Pokemon_yellow, you'll see that I was doing a lot of thinking about what it would take to effectively kill Unity. Like what happens there? And I do think, to be honest, it'll more so be a case of death by 1,000 cuts, right? Like Unity might do it to itself, so to speak. But that resulted in me picking up this open source engine called Godot. And anyway, I built, spoiler alert, Pokemon Yellow in Godot, picked up GDScript, which is like their scripting language, which kind of resembles Python. And it was honestly the most fun I've ever had programming. Like I had never done any game dev before, which is I think quite rare for programmers. It is the most fun way to write code because everything is interactive. Everything has a state, everything has physics applied to it, everything has relativity to one another. But anyway, it got me thinking, and I do think in gaming, and I'm a pretty big gamer, that there's this kind of rise of indie, so to speak. Like if you look at business models now, like Xbox with Xbox Game Pass, like people aren't talking about that enough, but Xbox has basically created Netflix for gaming. I've been a PlayStation guy all my life, and I picked up the latest Xbox, so I was like, this is cool. This is literally the dream. And as a result now, I'm actually playing a ton of these indie games that are built by studios with 2, 3, 4 people because I'm not forking out £60 each time to buy a new game, which would then just mean I would buy the latest iteration of FIFA. So there's that. I think the browser is going to unlock indie gaming like we can't even appreciate really yet. Like mobile did that to some degree, but wait till browser gaming becomes more of a thing thanks to WebGPU, etc. Because I mean, ultimately, the best distribution mechanism is the URL. And if gaming meets URLs, I think it's going to spread like wildfire. And then, I mean, look, the obvious point is these generative models are giving us a way to produce gaming assets, think sprite sheets, in seconds. Like when I built that Pokemon game, I drew pixel by pixel in a tool called Piskel, the sprite sheet for Ash Ketchum. It took me many hours. Like I remember my girlfriend coming in like hours later as she had been at her full day, and she's like, "Are you still drawing that thing?" So I think people are going to be able to, as 2 or 3 developers, build games that are hits like Among Us, right? But do it more often. The point being that Godot is increasingly the engine of choice for these indie developers.
This is not a podcast where we badmouth FIFA. So still, everyone go out and buy FIFA because it's an amazing game. But I'm very excited for the indie developers that are going to be doing FIFA in space or something like that, because that would still be fun to play too. But, thanks again, guys, Ian and Alex, for just spending the time and talking through all of these. I think people can find you. I'll link to your Twitters and your personal blogs and your podcasts so that everyone can see it. But I am an avid follower of Ian's podcast and Alex's blog. And so I highly recommend everyone else to subscribe, listen, and read them regularly because the insights that they've shared here are getting shared through the content that they're producing. Thanks again, guys. Really appreciate the time.
Thank you so much. It was a pleasure.
Thank you, man.